Welcome back to Very Ordinary Differential Equations. In this lecture, we continue applying second-order linear equations to topics, this time something known as motion under a central force. So let's suppose that we have a two-dimensional scenario, and at the point x, y, a force acting on an object is given by capital F of xy. Also, the magnitude of the force is only going to depend on the distance to the origin, and the force must either point directly towards the origin or directly away from it. These are our simplifying assumptions. In this scenario, it's natural to convert everything into polar coordinates. So x is going to be r cosine theta, y is r sine theta. R is the distance to the origin, and theta is the angle to our point from the positive x-axis. So any two-dimensional vector can be described by its magnitude and a unit vector in some angle. So our force is given by its magnitude times some angle vector. We've already declared that the magnitude of the force should only depend on r. So rather than saying the magnitude of f is given by the magnitude of f of r theta, it really just depends on f of r, just the radius. And the force vector is in the same direction as the origin. Okay, so whatever theta I'm pointing to, the direction of my force vector will be in the same direction. So capital F of r theta is given by some magnitude controlling function f of r, and the direction vector cos theta sine theta is the same theta as the point at which I'm acting. The origin, however, has no real well-defined theta, so we have to force f of 0 to be 0. In order for this to mean anything, if I wanted to let r be 0 to be at the origin, there's no real vector to put here. So the only option is to make it the 0 vector by making this 0. So our force function, capital F of r theta, is given by a force function f of r times the direction vector cosine theta comma sine theta. Newton's second law of motion states that force is mass times acceleration. So if an object is following the path r of t, theta of t, then x is given by r cosine theta, y is given by r sine theta. Then we obtain the mass times the acceleration should be exactly the force function. Now the vector notation implicitly relies on x and y, and we already know that polar coordinates are more natural for this situation. So rather than using 1, 0 and 0, 1 as the standard basis vectors, instead, we're going to use e1 and e2, cosine theta, sine theta, and negative sine theta, comma cos theta. So these unit vectors actually do depend on theta, but e1 points in the same direction as the force vector, cos theta, sine theta, directly away from the origin. And we immediately see that the dot product of these two vectors is 0, so they are in fact perpendicular. Furthermore, if I take d by d theta of e1, I end up with exactly e2. And if I take d by d theta of e2, I end up with exactly negative e1. So here are our two proposed alternate unit vectors. We've already seen that d by d theta of e1 is e2, and d by d theta of e2 is negative e1. Theta, remember, however, is a function of the parameter t. So if I throw the chain rule into the mix, if I want to take d by dt of e1, I can do d by d theta of e1 and then d theta dt. Similarly, d by dt of e2 is d by d theta of e2, d theta dt. We're going to use prime notation to specifically mean d by dt. So de1 dt is e1 prime, d theta dt is theta prime. But what's de1 d theta? We already know that de1 d theta is e2. So e1 prime is theta prime e2. And similarly, e2 prime is negative theta prime e1. So let's get back to talking about this central force function. We had determined that m times acceleration is given by the force. With our new notation then, this right here is just r times the e1 vector, cos theta sine theta. So m times the second derivative of this is given by f of r times e1. Let's now compute r e1 double prime using the product rule and our known results. So the first derivative by the product rule would be r prime e1 plus r e1 prime. But what was E1 prime? It was theta prime E2. If I take another derivative, I just need to take a derivative of what we just computed. Applying the product rule to all the terms in there gives us this long expression. But now I know what E1 prime is. I know what E2 prime is. So with those substitutions, we'll end up with this. Okay, remember E1 prime was theta prime E2, and E2 prime was negative theta prime E1. So I have a theta prime times itself. Now I just collect terms according to whether I have an E1 or an E2, and we have what we have at the bottom. So far we've determined that m times acceleration is the overall force, but we also computed this second derivative as such. Something times E1 and something times E2. So if we substitute that in for r E1 double prime, we'll determine two things. M times this must be exactly how many E1s I have. So m times r double prime minus r of theta prime squared must be exactly f of r. However, m times this should be 0 because I didn't want any E2s in there. But if m times something is 0, well then that thing is 0. So r theta double prime plus 2r prime theta prime should be 0. Now if I apply a chain rule to r squared prime, r squared prime will be 2r r prime. Now if I multiply this second line by r, we get r squared theta double prime plus 2r r prime. Theta prime equals 0. But that's exactly r squared theta prime prime. If I were to take this derivative, I would apply the product rule, and I'd say, okay, r squared theta prime prime, there it is, plus theta prime times the derivative of r squared. But the derivative of r squared is exactly 2r r prime. That's this term right here. So having multiplied this second line by r, I can replace it with r squared theta prime prime. If the derivative of something is 0, r squared theta prime prime was 0, then r squared theta prime was a constant h. We've therefore determined r squared theta prime is always h, a constant. But that's true for any time t. It's typically going to be easiest then to use t equals 0, because that's what our initial conditions will almost always be given as. So h must be r of 0 squared times theta prime of 0. Our initial position will usually be given by some x0, y0. But remember, x0 is r cosine theta and y is r sine theta. So if you're given x0 and y0, you can convert it to find your initial r and your initial theta. So our initial position is exactly r of 0 times cosine of theta of 0 comma sine of theta of 0. In other words, E1 of 0. Remember, E1 was the vector cos theta sine theta. Similarly, our initial velocity, well, if I take d by dt of all of this, we'll end up with r E1 prime, because that's just what this vector is. It's r E1. Applying the product rule, we get r prime of 0 E1 of 0 plus r of 0. What was E1 prime? It was theta prime E2. So this constant h is a pretty important thing that we should study. Let's first consider what if h is 0. Now h, remember, was r squared theta prime. If it's 0, it's always 0, and if it's 0 at t equals 0, we conclude either r squared is 0 or theta prime is 0. So either r of 0 is 0 or theta prime of 0 is 0. But remember, it wasn't just this constant for one value of t, it's the same constant for all values of t. So if h is 0, then for any time t, either r is 0 or theta prime is 0. So if r isn't 0, theta prime must be. So if r is 0 for an interval of time, r represented distance to the origin. So there is an interval of time at which the object is sitting perfectly still at the origin. But the only force points directly towards or away from the origin. We also had to specify that the force at the origin is 0. So if r is 0 for an interval of time, the object is sitting at the origin and experiencing no forces. That is the steady state solution. It will stay there forever. So otherwise, r might equal 0, but only at isolated points in time. Therefore, theta prime must be 0 for all other t's. Now, if theta prime is 0, then theta is constant. So any interval where I'm not at the origin, theta must be a constant, under the assumption on this entire slide that h is 0. So if h is 0, r squared theta prime must be 0. So if r is only 0 at isolated points, theta prime must be 0 on whole intervals. But if theta prime is 0 on an interval, then theta is constant on that interval. But if theta is continuous, it can't just jump from one constant to another. So if theta is continuous and it's a constant, then it's a constant, then it's a constant, it has to be the same constant. In other words, when h is 0, either you have your steady state solution of r is 0 and nothing happens, or theta is a constant. But if theta is a constant, then theta prime is always 0. So in the special scenario where h happens to be 0, the system reduces down to just be f of r, because theta prime is 0, theta is constant. Okay, so if theta is constant, this theta prime is just 0, and we just get mr double prime equals f of r. But since theta is constant, the angle to the origin is never changing. Okay, so the object just stays on a fixed line through the origin at a fixed angle. If we just reoriented ourselves so that that was the y-axis, we end up in a very simple situation. Our object just moves up and down. My double prime is f of y. When f of y is constant, this is our traditional approach to gravity. When f of y is proportional to y, we actually end up with a free undamped spring. When f of y is proportional to 1 over y squared, we get a more accurate approach to gravity. Okay, but overall, when h is 0, either steady state solution, hang out at the origin, never move, or angle never changes, and you may as well imagine that as just moving up and down, and that's a simpler scenario that we've already studied. So from this point forward, we're going to assume that h is not 0. This is the more interesting scenario. So how do we proceed under the assumption that h isn't 0? Well, if h isn't 0, then r of 0 can't be 0 and theta prime of 0 can't be 0. But then it's not 0 for all time. Remember that h is constant. In other words, r squared theta prime can never be 0. So theta prime can never be 0. Theta prime is d theta dt. It is our angular velocity. We never stop rotating. d theta dt is never 0. But furthermore, if theta prime has to be continuous, if it's never 0, it can never change from positive to negative. So if theta prime was ever positive, then it's always positive. And if theta prime is ever negative, then it's ever negative. In other words, whatever direction we begin our orbit in, we continue in that direction forever. Our direction never changes. Okay, our angular velocity cannot ever be 0, so if it's continuous, it can't change direction. But also, r of t is never 0. If r of t ever happened to be equal to 0, well then, here in our expression for h, I would get 0, but we know h isn't 0. So not only do we never stop orbiting in the same direction, we never pass through the origin. R will never be 0. Now, since h isn't 0, we concluded that r can never be 0. So we're going to define a new variable u to be 1 over r. Since r isn't 0, this is okay. I can define u to be 1 over r, in which case u squared is 1 over r squared. But remember that r squared theta prime was the constant h. Since u squared is 1 over r squared, I can manipulate this to get u squared is theta prime over the constant h. R is 1 over u. Okay, if u is 1 over r, then r is 1 over u. So I can take d by dt and get r prime is negative u prime over u squared. But u squared being theta prime over h allows me to change this to just be r prime is negative hu prime over theta prime. But the chain rule would tell us that du dt is du d theta dt. In other words, if I divide d theta dt over to this side, u prime over theta prime would just be du d theta. So r prime is negative h u prime over theta prime, but u prime over theta prime is du d theta. So r prime is negative h du d theta. So we've determined that r prime is negative h du d theta, where h is just some constant that isn't zero. If I take d by dt of both sides, now on the left we just get r double prime. The constant h I can factor out, and now I have to take d by dt of du d theta. Temporarily, let's just call du d theta to be w of theta. This makes it a little more convenient because now the chain rule says dw dt is dw d theta dt. In other words, w prime is dw d theta theta prime. So r double prime is negative h, this right here. dw d theta, since w was du d theta, is the second derivative of u against theta, but I did get this theta prime showing up. So r double prime is negative h, second derivative of u against theta, theta prime. But earlier we did discuss that theta prime is h times u squared. So plugging that in there, we end up with r double prime is negative h times hu squared, so negative h squared u squared, times this second derivative du d theta squared. So r double prime is negative h squared u squared d squared u d theta squared. So the original problem had been reduced to solving this. The mass m times r double prime minus r of theta prime squared should be f of r. But we've now determined that r double prime can be replaced in terms of theta. So we now have m r double prime minus r of theta prime squared equals f of r. In terms of u, r is 1 over u, so I replace that there, and I replace it here. I don't want r's and u's floating around since they're defined in terms of one another. Okay, here is our differential equation. Expanding this out, here we've just multiplied this by m. Here we've just multiplied this m, but remember we already determined that theta prime is hu squared. Okay, so now there are no d by dt's left. There is only d by d theta. Writing everything out, canceling what we can, okay, we end up with, okay, I'm going to multiply everything by minus 1, so this becomes positive, this becomes positive, this becomes negative. I'm not really doing anything here. Here we have a u squared squared over u, which we call u cubed. We can now rearrange this by dividing m h squared u squared out of both of these terms, giving us the second derivative of u plus u is this entire expression there. So let's just refresh everything we've said. We started off by assuming we have a force whose magnitude only depends on the distance to the origin and also points directly towards or away from the origin. We converted into polar coordinates r and theta. Then we threw Newton's second law into the mix and found that solutions to Newton's second law will exactly solve this equation right here, where u is 1 over r. So determining our overall mechanics has been reduced to this expression right here. A second derivative of u plus u equals a forcing function in terms of u. With all of that behind us, let's now derive Kepler's second law, that the area swept out by an object orbiting a central force will only depend on the length of time elapsed. It does not depend on where in the orbit you are, only the time elapsed. Well, let's suppose the object follows a path x of t, y of t, beginning at one time and ending at another. We're going to convert to polar coordinates, unsurprisingly. However, in polar coordinates, area is given by 1/2 r squared. So whatever our initial angle is and whatever our final angle is, we need to integrate 1/2 r of theta squared d theta. If we change variables back to t, however, when theta was theta of t1, time was t1. When theta was theta of t2, time was t2. Otherwise, I'm replacing theta with theta of t, and d theta is theta prime of t dt. So I've converted this back to be an integral in terms of time, t. Having converted back to our variable t, we now have this as our area. In our system, however, remember that in this central force scenario, r squared theta prime is a constant h. And what are we integrating? R squared theta prime. Therefore, we're just integrating h. And integrating h is pretty easy. It's just h times the length of the interval, t2 minus t1. And of course, we had this factor of 1/2 out in front. We've therefore derived Kepler's second law. In a system of motion governed by a central force, a line joining the origin to a moving object sweeps out equal areas in equal intervals of time. How have we shown this specifically? In our system, the area swept out from t1 to t2 was given by exactly a constant h times t2 minus t1 over 2. Since h is constant, the only thing that affects this area is the length of time t2 minus t1. So if I changed those times but kept the difference between them the same, I would get the same area. That's Kepler's second law. Also, it's worth pointing out, this holds in any system of central force. It's not just a question of inverse square gravity. Any system with a central force law will satisfy Kepler's second law. The area swept out depends only on the length of time. As a second example, determine the behavior of an object orbiting a central force where the force is proportional to the inverse square of the distance. So now we're making a specific assumption about our force function f. The magnitude is proportional to the reciprocal of the square of the distance to the origin times the mass of the object, and the force points towards the origin. So f of r, the magnitude of our force function, points towards the origin, so it's negative, and it's m times a constant k divided by the distance r squared. So our system had been transformed into all of this, but now f of r has a very, very specific form. So since f of r is negative mk over r squared, in our differential equation, if I change r to be 1 over u, we end up with f of r is negative mk over r squared, but since r squared is 1 over u squared, it's going to cancel that one right there. This m cancels that one, this negative cancels that. So overall, the second derivative of u d theta plus u is just k over h squared, where k and h are both constants. So here we have it, d squared u d theta squared plus u is k over h squared. This is now a differential equation governing motion under a central force where the central force is proportional to the inverse square of the distance. So our differential equation has been simplified quite a lot. Solutions to the complementary equation are easy to come by. U double prime plus u equals 0. We just get u of theta is some multiple of cosine theta plus some multiple of sine theta. We can convert this to amplitude phase form. Its amplitude is capital A, and it's a cosine of theta minus a phase angle phi. The forcing function k over h squared is just some constant. So we can really quickly see that a particular system could be given by up is the same constant. Its second derivative will be 0. U is the constant. We get out the constant. Okay, so a general solution is given by one of these cosine functions plus this exact constant k over h squared. And this is u of theta. So u of theta is a cosine of theta minus phi plus the constant k over h squared. Let's convert all of this back to polar coordinates. U was 1 over r, so r is 1 over u. Here it is, 1 over u. We can rewrite this as r is rho over 1 plus e times the cosine of theta minus phi, where rho is h squared over k. So if I multiply by h squared over k, that numerator would become that. And this constant e is just a rho. Using e as the constant is really not ideal, but it is for some reason typical in this context. So e here does not represent the base of the natural logarithm. It's simply the amplitude of this cosine curve times the same rho. So here's the solution we found. R is a constant over 1 plus a constant times the cosine of theta minus phi. In other words, it only actually depends on theta. The only variable there is theta. In other words, if an object is orbiting around the center, if it comes back to the same angle, theta, it must have come back to the same radius r. If this angle theta comes back to the same thing, or it plus 2 pi, r will have to be the same. So whatever path our object takes, in any particular direction, theta, it will achieve at most one distance r. Okay? If the path of the object is traced out, it will never achieve two different radii at the same angle. If the angle comes back to be the same, then so will the radius. So here was our solution again. Note again, it depends only on the variable theta. Rho and e and phi are all constants. So the curve here is a conic section. The positive constant e is the eccentricity of this conic section. This is why it's used the letter e. It's not the base of the natural logarithm, it's the eccentricity. If the eccentricity is less than 1, so capital A times rho is less than 1, the curve is an ellipse. One of the foci of the ellipse is the origin. When e is equal to 1, the curve is a parabola, and the 1 focus is the origin. And when e is bigger than 1, the curve is actually a hyperbola with one of the foci at the origin. In the case of an ellipse, what are the minimum and maximum values of r? What are the closest and furthest from the origin that the object gets? Well, r will be minimized when this denominator is as big as possible, or when the cosine curve hits a 1. So I have rho over 1 plus e. But r will be maximized when the denominator is as small as possible, or when cosine is minus 1. So the maximum radius is rho over 1 minus e. So depending on capital A, h, and k, you compute rho and e. The closest the object gets is given by this formula. The furthest the object gets is given by that one. As a third example, let's determine the initial conditions required for an object to achieve a circular orbit under an inverse square central force. So here was the solution we found in the previous example. A circle is a conic section with 0 eccentricity, in which case the radius would just be rho. What initial conditions will result in 0 eccentricity? So we rewrite r and theta to be functions of t. R of theta of t is now written as rho over 1 plus the eccentricity times the cosine of theta of t minus phi. And let's suppose we have initial conditions. R naught theta naught is our initial radius and angle. R prime of 0, theta prime of 0 is our initial derivatives. So r of theta was given by this function here. Setting t equal to 0 and observing that r of theta of 0 should be r of 0 gives us r sub 0 is rho over 1 plus the eccentricity times the cosine of theta naught minus phi. We directly get that this eccentricity is 0 if and only if r naught is exactly rho. But since rho is h squared over k, and h was r squared theta prime, which was r naught squared theta prime naught at time t equals 0, to obtain an eccentricity of 0, we need r naught to be rho. In other words, we need rho to be h squared over k, but h is this. At time t equals 0, it's that. What's necessary to happen? R naught should be rho, h squared over k, but here's h squared over k. So in order for r naught to equal all of this, what we need is for r naught cubed times theta prime naught squared to equal k. I can cancel one factor of r naught out here. So k has to be a very specific constant. So again, here is our solution for r as a function of theta of t. If we take the derivative d by dt, okay, it's a bit of work, but this is what you'll end up with. Under the assumption that h wasn't 0, we already know theta prime here and theta prime here will not be 0. So the eccentricity will be 0 if and only if r prime theta of t, theta prime t, equals rho eccentricity theta prime t sine over 1 plus eccentricity cosine of all of this. Setting the eccentricity to be 0 makes this entire thing 0. Since theta prime isn't 0, r prime of theta of 0 must be 0. So overall, how can we have a circular orbit? How can we have 0 eccentricity? We determined that setting initial conditions in these terms must have r prime of 0 equals 0, but r of 0 cubed times theta 0 prime squared must be the constant k. The first condition is pretty clear. If we want a circular orbit, your initial radius shouldn't be changing. I shouldn't start with r prime positive or negative. I shouldn't start moving towards or away from the origin. Otherwise, I'm definitely not going to have a circle. The second condition balances a few things against one another. The starting distance, r sub 0, the starting angular velocity, theta prime sub 0, and the constant k, which came from a gravitational force. Overall, what have we done? Under the assumption that the force acting on an object depends only on the distance to the origin, and that force is always in a direction directly towards or away from the origin, we can study the resulting system of motion. The problem began in several dimensions. We had x's and y's as a function of t. However, we were able to determine with these simplifying assumptions that r, the distance to the origin, is purely a function of theta, the angle in polar coordinates. We were able to derive Kepler's second law of planetary motion. Objects in orbit sweep out areas at a constant rate. We also studied the special case of the force being proportional to the inverse square of the distance, which is a realistic model for gravity. Orbits in this realistic gravitational scenario are conic sections. They can be ellipses or circles or parabolas or hyperbolas. Circles required extremely specific initial conditions. Okay, but generally you're either going to get ellipses or hyperbolas. Parabolas was also one specific value of the eccentricity being exactly 1.